Imagine waking up tomorrow. The weather outside is not unusual, not dramatically cold, not stormy, just slightly off, a little cooler than last February, a little drier than last spring. You brush it off. Seasons change. Then the next year, same thing, and the year after that. And 5 years later, your country is importing food because the farmland that used to reliably produce crops is no longer doing so. 10 years later, the coastline your grandparents grew up visiting is underwater. Not because of a storm, not because of a flood, because the baseline shifted and nobody caught it in time. 20 years later, the winters your children's children experience are unlike anything in recorded human history. Not because of a single disaster, not because of a bomb or a war or a meteor, but because of something that happened quietly under 3 kilometers of ocean water in a system that most people have never heard of and almost nobody fully understands. That is not a movie plot. That is the scenario a group of researchers in the Netherlands just made a serious scientific case for. And the reason it is worth your full attention today is not because it is certain. It is not certain. The reason it matters is because the argument they made this week does not just add to what we already knew. It changes the question entirely. The question they changed is one that scientists, governments, and the public have been organized around for 20 years. Here is what I am going to do in this video. I'm going to tell you exactly what the system is, why it matters more than almost any other structure on the surface of this planet, what the new research actually says and what it does not say, who disagrees with it, and why their disagreement is serious and not just noise, what the actual data from the real ocean shows right now, what happens to life in the northern hemisphere if this goes wrong, and what the 3 specific things are that will resolve this argument over the next few years. No hype, no catastrophizing, no false reassurance either. Just the full picture, including the parts that are deeply uncomfortable, because they are uncomfortable in a specific way that the usual climate conversation misses almost entirely. Let us start with what is actually being measured, because most of what circulates publicly about this system is either outdated or was never accurate to begin with, and you cannot evaluate the new research without understanding the baseline. The Atlantic Meridional overturning circulation is a massive loop of water movement that spans the entire Atlantic Ocean, from the tropics to the Arctic, and from the surface down to depths of 2 and 3 kilometers. Warm, salty water at the surface travels northward through the Atlantic. When it reaches the high latitudes near Greenland and the Nordic seas, it releases its heat into the cold atmosphere above. That release of heat changes the water. It becomes colder, denser, heavier, and heavy water in the ocean does what heavy things do. It sinks. When it sinks, it begins a return journey southward at depth, traveling 2 to 3 kilometers below the surface, moving slowly and silently back toward the tropics, where the cycle begins again. That loop is the largest heat-moving structure on the surface of this planet. At 26.5 degrees north latitude, where a network of instruments has been recording it continuously since April 2004, the mean strength of that circulation measured across nearly 2 decades is 17 sverdrups. 1 sverdrup is 1 million cubic meters of water per second. 17 sverdrups is 17 million cubic meters per second moving northward. To give that number some shape, every river on this planet combined carries roughly 1 sverdrup. This circulation carries 17 times all of that combined, across a single line of latitude, every second of every day, without pause. A separate analysis produced a figure of 16. 9 sverdrups from a slightly different time window. The 2 measurements agree, which matters because agreement on the baseline is what makes disagreement about the trend scientifically meaningful. The heat that current carries northward across that line is 1. 2 petawatts. A petawatt is 1 quadrillion watts. 2 petawatts is approximately 100 times the entire energy consumption of human civilization, delivered continuously northward by moving water. This is why cities like London and Edinburgh and Bergen sit at the same latitude as parts of Siberia and northern Canada, but experience winters that are incomparably milder. That circulation is not a contributing factor to the climate of northwestern Europe. It is a foundational condition of it. Remove it, and the arithmetic of the climate in those regions changes in ways that the infrastructure, the agriculture, and the societies built there are not designed to handle. And for brief windows across the past 22 years of continuous measurement, the instruments have recorded that system running backwards. Not slowing, running backwards. -4. 3 sverdrups. The mean is 17 positive. The range over 10-day windows swings from -4. 3 to +32. 3. That variability is enormous, and it is the root of almost every scientific disagreement you will encounter in this video. Keep that range in your mind because it will matter later. Now, here's where this week becomes important. Researchers at Utrecht University ran the same climate model twice. Same physics, same ocean, same starting conditions, same model doing the same job, beginning from the exact same place. The only thing they changed was a single variable. how fast they added carbon dioxide to the atmosphere. In the first run, carbon dioxide rose at 5 parts per million per year. That is slow. It is deliberately, unrealistically slow, much slower than the atmosphere is actually doing. The authors were explicit about this. They designed the slow run not to be a realistic scenario, but to isolate the effect of rate alone. In the second run, carbon dioxide rose at 5 parts per million per year. That is roughly the rate of the actual present day. Everything else was identical. Same model, same resolution, same ocean physics, same initial state. The only variable was how hard the pedal was being pressed. In the slow run, the Atlantic circulation survived 4 degrees of warming. It survived 5 degrees of warming. It did not collapse at all. In the fast run, it collapsed at around 2 degrees of warming. Read those 2 sentences again, because the implication is stranger and more consequential than it first sounds. The same ocean, warmed to the same temperature, either survives or collapses depending entirely on how fast it got there. Temperature alone does not determine the outcome. In this experiment, temperature does not even come close to determining the outcome. The rate of warming determines the outcome. For 2 decades, the entire public argument about the circulation has been organized around finding a temperature threshold. How many degrees of warming before it breaks? 2, 3, 4? Every headline, every model study, every expert disagreement, every policy document has been structured around answering that question. This paper says there is no such number. The circulation does not have a temperature threshold it cannot cross. It has a speed limit, and the speed limit the authors identify as approximately 0.3 of a degree Celsius per decade. Below that rate, in their experiment, the system tracks the changes happening above it. The surface warms, the signal propagates downward, the density structure adjusts, the circulation finds a new stable configuration. Then the process repeats. Under slow forcing, the system is never far from equilibrium. It walks step by step into a warmer world, and at every step it is standing on solid ground. Above that rate, the communication between the surface and the deep never completes. The surface changes again before the deep ocean has finished responding to the last change. The system is permanently chasing a target that keeps moving faster than it can follow. It is never in equilibrium, never stable, never standing on solid ground. And at some point, it stops chasing altogether. The authors call this failure to track a stable state. That phrase is important. This is not a tipping point in the dramatic, cliff-edge sense the word usually carries in popular writing. It is a system gradually losing its ability to keep up with conditions above it until the gap becomes too large to close. To understand why rate matters so much more than level, you have to understand something about how the ocean's layers respond to changes. The surface of the ocean responds to the atmosphere over weeks and years. The deep ocean, the 2 to 3 kilometers of water that the return flow moves through, responds on timescales of centuries. Water that sinks in the North Atlantic today may not see the surface again for 1,000 years. The surface and the deep are not one system on one clock. They are 2 systems on vastly different clocks. Under slow warming, both clocks have time to run. Every small change at the surface eventually gets communicated downward, and the deep ocean reorganizes to accommodate it. Under fast warming, the surface clock keeps advancing, while the deep ocean clock barely moves. The gap between where the surface is and where the deep has managed to adjust grows continuously larger. At some point, the adjustment mechanism cannot close that gap fast enough to maintain the density contrast that drives the sinking. And the sinking is the engine. Without the sinking, the loop breaks. One of the authors offered a metaphor that is worth keeping. If you are driving toward a wall, you can steer around it, but steering requires braking. If you keep pressing harder on the accelerator, you run out of road before you can redirect. The argument in this paper is not that collapse is certain. It is that the world is pressing the accelerator at exactly the moment when braking matters most, and that the consequences of not braking operate on a logic the temperature conversation does not capture. This brings up something even more uncomfortable, and it lives right at the center of how the world is currently thinking about climate strategy. A very large part of current international climate policy is built on what are called overshoot pathways. The logic works like this. We will probably exceed 5 degrees of warming, possibly 2 degrees, for a period of time. Then, through massive emissions cuts and eventually through large-scale carbon removal from the atmosphere, temperatures will be brought back down. The peak is treated as a temporary condition, a detour. The final destination is what counts, not the route taken to get there. If the stability of this circulation depends on the rate of change rather than the peak level of warming, that framework has a hole in it that is difficult to patch. A fast overshoot corrected later is not the same as never overshooting. The damage to a rate-sensitive system is done during the fast part. The deep ocean does not know you plan to come back down later. It only knows how fast the surface moved. You cannot unring that bell by arriving at a lower number afterward. The path matters, not just the destination, And if this rate dependence holds up under independent scientific scrutiny, it means some of the most widely adopted climate strategies in the world are designed around a metric that does not describe the most important risk. Now I need to be precise about what this research is and what it is not, because precision matters here more than it does in most science conversations. This is one paper that used one model at 2 ramp rates. That is a clean, honest, well-designed experiment. But it has not been independently replicated. The test that transforms a result from provocative to established is replication in an independent Earth system model built by a different group, using different code, different parameterizations, different assumptions. That test has not happened yet. Other modeling groups will run this experiment. That is exactly what should happen. And when the results come in, they will either confirm that the rate dependence is a real property of the physical system, or they will find that it is a feature of this particular model and not a general truth. Both outcomes matter. Both deserve coverage. The real ocean is also being measured, and that data does not live in a model. It has been measured continuously since April 2004, when the rapid array was anchored across the Atlantic at 5 degrees north. For 22 years, without interruption, those instruments have been sampling the flow. And 22 years sounds like a long time until you put it against the system. This circulation varies on timescales of 30 years, 40 years, 60 years. Natural internal cycles that stretch across multiple decades make it genuinely difficult to separate a long-term trend from one phase of normal variation within a record that only covers 22 years. This is not a technicality invented to avoid a conclusion. It is the honest heart of the entire scientific dispute, and it deserves to be stated directly. Some researchers, looking at this data and at older proxy evidence from sediments and corals, argue that the circulation has been slowing since the middle of the 20th century. Others, looking at the same data and applying different statistical methods, argue there has been no measurable weakening since the 1960s. That second position was published in Nature Communications. It is not a minority fringe view. It represents a genuine scientific disagreement between serious researchers working from the same underlying measurements. Anyone who tells you this is settled in either direction is telling you something the current evidence cannot support. That is not a dodge. That is the actual state of the science, and it matters. Because the rate argument from Utrecht only becomes policy relevant if something is actually happening in the real ocean, not just in models. But there is an observational result from earlier this year that deserves more attention than it has received. A team led by researchers at the University of Miami's Rosenstiel School published in Science Advances. They looked at 4 separate ocean monitoring arrays along the western boundary of the North Atlantic. These arrays use instruments anchored to the seafloor and bottom pressure sensors to estimate the deep southward flow below roughly 1,000 meters depth. 4 arrays, independent of each other, measuring at latitudes from 5 degrees north to 5 degrees north, a span of 26 degrees of latitude across the North Atlantic. All 4 show a decline, consistently, in the same direction, across that entire range of latitude. That is the part that matters most. A decline at one array is ambiguous. It could be natural variability. It could be a local shift in where the flow is concentrated at any given moment. But a consistent decline, measured independently at 4 separate locations, spanning more than a quarter of the Atlantic's north-south reach, is much harder to explain that way. The authors described it as suggesting a basin-wide shift rather than a short-term fluctuation. They proposed these western boundary measurements as an early warning system, a tripwire that would register something structural before it becomes irreversible, not a prediction of collapse. A canary, something that tells you the direction things are moving before you know how far they will go. Now here's the other side, because the other side is serious and has a serious physical argument behind it, not just reassurance. The Met Office and the University of Exeter published a study in Nature in early 2024 with a headline that was deliberately blunt. Climate change, AMOC, likely to withstand future warming. The lead author described a circulation that resists the pressures of rising temperatures and increased freshwater input from melting ice. Their mechanism is not statistical, it is physical. Under extreme warming scenarios, their model produces an overturning circulation in the Pacific Ocean. But the Pacific circulation is not strong enough to balance all the wind-driven upwelling happening in the Southern Ocean. Something has to compensate for that imbalance. And in their simulations, the compensation comes from maintained sinking in the North Atlantic. The physics of the Southern Ocean effectively requires the North Atlantic to keep working. A complete shutdown is prevented not by the North Atlantic's own robustness, but by what the rest of the ocean needs it to do. A researcher from Exeter described his position with a line that captures expert calibration better than any summary. He said he thought it very unlikely his house would burn down in the coming years, but he still buys insurance. That is not dismissal of the risk. That is a scientist saying that something can be unlikely and still worth protecting against. And he was also careful to say that his result does not rule out weakening. His model still shows weakening over this century. What it suggests is that complete collapse in the next 75 years is unlikely under current forcing. That is a more confident position than the Utrecht paper implies, but it is not the same as saying nothing is happening. The Ditlevsen and Ditlevsen result from 2023, published in Nature Communications, produced the number that has been quoted most widely in coverage of this topic, a median tipping year of 2057. That number appears constantly and almost always without the context that makes it meaningful. The 95% confidence interval around that median runs from 2025 to 2095. That is a 70-year window. Quoting the median without quoting the range converts a statement of deep scientific uncertainty into a date on a calendar. That is not what the paper said. The paper said the median estimate was 2057 inside a range so wide that the researchers were explicitly uncertain about nearly everything except the direction. That result also drew substantive technical criticism. The UK Science Media Centre gathered expert reactions, questioning the robustness of the early warning signals the statistical analysis relied on. In October of that same year, 44 climate scientists signed an open letter to the Nordic Council of Ministers, arguing that the risk of disruption to this circulation was being systematically underestimated in policy discussions and demanding a formal government-level assessment. That assessment was published earlier this year. It was the first time any government body treated this specific risk as a matter requiring a policy response, rather than leaving it solely to academic journals. There is one more piece of intellectual honesty from this field that deserves credit because it almost never makes it into public discussion. Climate models are known to simulate a version of this circulation that is more stable than the real ocean appears to be. To compensate for this known bias, researchers add artificial freshwater inputs to their models to push the simulated circulation into a regime that better matches what the instruments are actually measuring in the real Atlantic. One of the Utrecht authors said this directly and without apology. What it means is that the results produced by these models, including the most widely cited projections from international assessments, are controlled experiments about the physics of the system, rather than literal forecasts of when a specific thing will happen. That distinction matters for how you interpret anything that comes out of climate modeling of the circulation, including the Utrecht result. So what actually happens to the world if it collapses? The most detailed modeling of European consequences comes from a study published last year. A model world with roughly 2 degrees of warming and a collapsed circulation was projected forward. The city level numbers are genuinely difficult to hold in mind. London, a mean winter temperature near 1, 9 degrees Celsius, with 1 in 10 year cold extremes reaching around minus 19. Edinburgh, a 1 in 10 year extreme of nearly minus 30. Paris, approaching minus 18 in rare cold events. Oslo, mean winter temperatures around minus 16. 5 degrees Celsius, with maximum daily temperatures below freezing for 169 days a year, and 1 in 10 year extremes approaching minus 48. February Arctic sea ice reaching the coastlines of Scandinavia and much of Great Britain. One researcher described those winters as like living in an ice age. Another noted something that the frozen Europe narrative usually leaves out. Summer temperature extremes in those scenarios are barely affected at all. The collapse does not make the whole year cold. It makes the winters extreme, while summers remain relatively unchanged. That radical increase in seasonal range, in the swing between the coldest and warmest parts of the year, is something the infrastructure, the agriculture, and the energy systems of those regions have not been designed to handle. Cold snaps of minus 30 in a country built for mild winters is a different category of problem than cold snaps of minus 30 in a country that has always had them. But there are consequences that matter to far more people than those living in northwestern Europe, and they receive a fraction of the attention. On sea level, research published this year in the journal Ocean Science found that as the circulation weakens, dynamic sea level rises sharply across the North Atlantic, reaching rates of 6 millimeters per year over a century and up to 4 millimeters per year near densely populated coastal regions along the eastern United States. For comparison, the current global mean rate of sea level rise is 3 millimeters per year. 4 millimeters per year sustained across a century is 40 additional centimeters on top of everything else sea level is already doing from thermal expansion of the ocean and melting land ice. The mechanism is straightforward. The Gulf Stream system tilts the ocean surface as it flows, pushing water away from the American coastline. Weaken that tilt and the water redistributes, piling back against the eastern seaboard. On rainfall, a comparison of 4 separate climate models published in the journal Earth's Future found consistent and large changes to the tropical rain systems that billions of people depend on. Under a collapse scenario, the ensemble mean annual change to the West African monsoon is a decline of 29%. The Indian summer monsoon declines by 19%. The southern Amazon gains 44% more precipitation. All four models agree on the direction of change: a southward shift of the tropical rain belt, drier across the northern tropics, and wetter across the southern tropics. The magnitude varies significantly across the models, with one showing a 50% wet season decline in West Africa, while others show 5 to 10%. The direction is consistent. The scale is not yet settled. But even the conservative end of that range, applied to the agricultural and water systems of West Africa and South Asia, represents a massive disruption to food and water security for populations that already have limited capacity to adapt. On agriculture, closer to the regions most directly affected by cooling, a study modeled Great Britain specifically under a collapse scenario. Average temperature drops of around 4 degrees, substantially less rainfall, arable farmland reduced by roughly a quarter, and annual crop value falling by an estimated £346 billion per year. The authors describe those losses as an order of magnitude larger than the agricultural losses expected from climate change without a collapse. They assessed large-scale irrigation as a compensating measure and found it prohibitive on both the volume of water required and the infrastructure cost at the necessary scale. There's also a feedback that closes the loop in an uncomfortable way. Research from the Potsdam Institute for Climate Impact Research found that a shutdown of this circulation would release carbon currently stored in the deep ocean back into the atmosphere over hundreds of years, adding roughly 0.2 of a degree of additional warming on its own, independent of anything else happening at the surface. The collapse would contribute incrementally to the very warming that stresses every other connected system. Now, let me be precise about what those consequences actually represent, because the way they get applied to arguments matters. A researcher at the National Oceanography Center pushed back specifically on how the Frozen Europe study gets used. The numbers that come out of that work describe European climate 200 years after a collapse, not the years and decades immediately following one. The transition itself is not what the study models. And in high-emission scenarios, greenhouse warming does not simply stop because the circulation weakens. In that version of the experiment, the warming effect of continued emissions outruns the cooling effect of the lost circulation. And Northern Europe still warms year-round, just less than the global average. Collapse does not automatically produce a frozen continent. What it produces depends entirely on which world the collapse happens in and how fast emissions continue after it. So where does all of this actually leave us, and what will resolve this? 3 things are worth tracking specifically because they are checkable and will either strengthen or weaken the case over the next few years. The first is replication. The Utrecht result rests on one model at 2 ramp rates. That is a clean experiment, but it is one result. Independent modeling groups will run the same comparison using different climate models. If the rate dependence holds up across those independent tests, it stops being a provocative finding and starts being an established property of the physics of the system. If it does not replicate across different models, it stays scientifically interesting but loses its power to change how we should think about the risk. The attempts will happen. They are probably already underway. And when results emerge, they deserve coverage regardless of which direction they point. The second is the ocean array data. The Miami team proposed their 4-array western boundary measurements as an early warning system precisely because they update. If the decline they found consistently across 26 degrees of latitude continues in the next annual data release, the argument that this reflects a basin-wide structural shift rather than natural variability becomes considerably stronger. If the trend flattens or reverses, that is equally important and deserves equally prominent reporting. The data does not have a preferred conclusion. It only records what is happening. The third is policy. The Nordic Council assessment stated plainly that current climate adaptation plans have not been developed with the specific possibility of tipping point crossings in mind. Whether other governments commission similar assessments, and whether the overshoot logic that currently dominates international climate strategy gets reconsidered in light of a rate-dependent threshold rather than a temperature-level threshold, is a concrete and observable question that will develop over the next year or 2. It is no longer only a scientific question. It is a political one about whether the people making decisions about emissions pathways are working with the right mental model of what the most serious risks actually are. Here is what I would take from all of it. The circulation is being measured continuously and without interruption. And the most recent analysis of 4 independent western boundary arrays found a consistent decline across 26 degrees of latitude. That consistency is hard to dismiss as noise. The record those measurements come from is 22 years long against a system that varies over decades and responds fully over centuries, which is why serious scientists still disagree in published journals under their own names. That disagreement is not a scandal. It is the honest state of a field grappling with a system that is genuinely difficult to observe and genuinely complex to model, and where the stakes of being wrong in either direction are severe enough that intellectual honesty matters more than a clean narrative. What changed this week is the shape of the question. For 20 years, the entire public and scientific conversation about this system was organized around temperature. How hot before it breaks? 2 degrees? 3? 4? The entire policy and media architecture around this risk was built on finding that number. 3 researchers in Utrecht just made a serious, peer-reviewed, published case that the question itself was wrong, that what matters is not how warm the planet gets, but how fast it gets there. And that the speed limit they identified, roughly 0.3 of a degree Celsius per decade, is not a distant boundary we might someday approach under extreme scenarios. It is approximately the rate the world is already approaching on the trajectory it is currently on. That is not a prediction of collapse. Nobody serious is claiming collapse is certain. What it is a warning that we may have been watching the wrong dial for 2 decades, and that the right dial, the rate dial, may already be showing something we did not know to look for. We will be tracking the replication attempts and the next data releases from the ocean arrays as they come in. This is not the last word. It is a reframing. And reframings, when they are this precise and this testable, are exactly what science is supposed to produce.